Okay, quick set on ideal gases. And hopefully most of this you've talked about in chemistry, and so it's just a review. But we'll start with the ideal gas law. And the ideal gas law says that in an ideal gas, it always follows this equation that we see here, which is PV equals nRT. And in this particular equation, P is the pressure of the gas. That's this right here. V is the volume of the gas. N is the number of moles of gas. R is a constant, the universal gas constant, which is down here at the bottom, 8.31 joules per mole Kelvin. And T is the temperature. And so notice with this that if we have PV equals nRT for a given sample of gas, obviously R, because it's a constant, is going to be the same. And if we have a specific sample, the number of moles of it's going to be the same. So the N is going to be the same. And so this NR is a constant, which is equal to PV over T. Now, this PV over T, pressure, volume, and temperature relationship, leads us then to our other gas law, which hopefully, again, we remember from chemistry. The first one, which is Charles' law, we don't actually have written here, but this is V1 over T1 equals V2 over T2. Okay, and this one says that the volume is directly proportional to its absolute temperature. Okay, volume is directly proportional to the absolute temperature. And so at a constant pressure, if you increase the temperature, you increase the volume. And if you decrease the pressure, or decrease the temperature, you decrease the volume. The second one, Boyle's law, talks about what happens at a constant temperature. And if the temperature is fixed and we change the volume, we change the pressure. If we increase the volume, we decrease the pressure. If we decrease the volume, we increase the pressure. And that's our P1V1 equals P2V2. And then the final one is the pressure law, which simply says that a constant volume, if we change the temperature, we change the pressure, and this is again directly proportional. So if we increase the temperature, we increase the pressure. And then also notice then that this leads us to our combined gas law, and this also comes really from the ideal gas law, and it simply says that P1V1 over T1 equals P2V2 over T2, and remember that these are all actually equal to that Rn constant, or that Nr constant, but this ties them all together. And then if one of these three variables is constant, obviously then it just falls out of the equation. But that's what we're talking about, ideal gases, and we use that as a model a lot of times, but real gases are not ideal gases. They conform to the characteristics of ideal gases in certain situations, and there's certain limited conditions, but they can condense, they can solidify, a lot of different things can happen. If the sample is too big or too small, it's not going to behave as an ideal gas. So it's important to be aware of that and to understand the differences. Ideal gases ignore all of the forces in between the particles, and in reality there are some forces in between the particles. Okay, and it's possible to get most real gases to behave as ideal gases, as we said, in certain conditions. These conditions generally being low pressure and very high temperatures. And so that type of situation tells us that there's a if it's low pressure, it's generally not a lot of gas molecules, or the volume in which we're looking at is very large. And if it has a high temperature, the molecules are moving so fast that those intermolecular forces don't really come into play as much. You can, even as insignificant as they are, normally when you have high temperatures and those molecules are moving so fast and they have so much kinetic energy, then the intermolecular forces, the effect those have decreases even more till it's almost none. And then inversely or conversely, at high pressures and low temperatures, real gases behave most differently from ideal gases. And so in the opposite situation, you get the most difference between the two. This idea of the relationship between volume, pressure, and temperature also led to really to the establishment of the Kelvin scale. And so what scientists did was they started making all these measurements of temperature and pressure and volume, and ended up plotting temperature against volume, and this gave them a linear fit. They carried it back, okay, and that's what we're talking about when we talk about extrapolation. So we have volume and temperature, and they got it as cold as they could. They saw it was this nice linear fit, and then they started working backwards. And they realized that at some point, the volume of the gas would eventually reach zero. And when they looked at it in terms of pressure and temperature, they saw the same thing. There was this linear relationship between pressure and temperature, and if they carried it back, they extrapolated back, at some point the pressure also dropped to zero. And this is what they called absolute zero. And so even now, even today, we still haven't reached absolute zero. We've gotten very, very, very close. Within fractions of degrees, we've never reached it, and the idea is that it's probably going to be impossible to reach because of laws of physics. But there's this theoretical temperature where the volume of the gas would drop to zero, the pressure would drop to zero, and we call that absolute zero, and it's from which the Kelvin scale is derived. And we have no negative temperatures on that scale, but it's negative 273 on the Celsius scale.